Okay, today's topic is going to be solving exponential equations, a topic taken from college algebra. My name's Kurt Overhiser, and I'll be your host for this topic as we work some examples and show you some steps in how to proceed in solving exponential equations. The first example that we will look at together will be to solve the following equation. This equation is 9 times 3 raised to the x minus 4 power equals 27 raised to the negative x power. This is the first type of equation that we're going to look at, where there's another type that we're going to look at that requires the use of logarithms. This one doesn't. The reason why is because if we look carefully at the 9, the 3, and the 27, all of those can be expressed as powers of 3. And so what we do is we first want to express them as powers of 3. So if you look at 9, if you realize that 9 is equal to 3 squared, we'll leave the 3 to the x minus 4. And then 27 is also a power of 3. 3 to the third power is 27. So if this is 27 raised to the negative x power, that would be the same as saying 3 to the third, which is 27, all raised to the negative x power. Okay, so we have everything in terms of a power of 3. So next what we're going to do is we're going to use the rules of exponents to simplify each side. We got 2 bases of 3 on the left hand side, and if we simplify that we can make that down to 1 base, because we're going to use the rule of exponents that says when you multiply quantities in the same base you add their exponents. So this would be 3, and then if we take 2 and we add it to x minus 4, we get 2 plus x minus 4. We're going to use another rule of logarithm, and the other rule of logarithm that we're going to be using on the other side of the equation is we're going to be multiplying the 2 exponents together, because when you take a power and in turn raise it to a higher power, you remember from intermediate algebra that you have to multiply the 2 exponents together. So the right hand side would be 3 to the negative 3x power. I take the 3, multiply it by negative x, and I get negative 3x. Okay, and then 2 plus x minus 4 is x minus 2, and that's equal to 3 to the negative 3x. Okay, so I have one base of 3 on the left-hand side, 1 base of 3 on the right-hand side, and so what we do now is, because exponential functions are one-to-one, what we can do is we can drop the bases and we can just equate the exponents equal to each other. So if we just look at just effectively ignore the base and just look at the exponents, and if we take those exponents and set them equal to each other, we get this equation. X minus 2 equals negative 3 times x. We can only set the exponents equal to each other when the bases on each side are the same, and there's only 1 base on each side. So in this case, we have 1 base of 3 on the left, 1 base of 3 on the right. They're both the same base, 1 on each side. Then you can go ahead and equate the exponents. And then at this stage, now that the exponents are equated, we go ahead and solve the equation for x. So if I add 3x to both sides, I would get 4x minus 2 equals 0. Add 2 to both sides and divide by 4. And you get x is equal to a half. And then that would be our answer right there. So just to kind of document these steps, what we just did in this first example, we can kind of put the steps right here on the margin and the side. Step number 1 would be to use a common base for both sides of the equation. So this right here is really step number 1. We had base of 27, 3, and 9, and the least common base is 3, and so we expressed all the bases as powers of 3, and that's what it means to use a common base for both sides of the equation. Step 2 is to use the rules of exponents to simplify each side of the equation, and then the key here is to have one base for each side. Okay, this is step 2 right here, if we label it. We had 2 bases of 3 on the left-hand side, but we used the rule of exponents where you add the exponents, and then you can bring that down to, consolidate that down to 1 base of 3. And the right-hand side already had a base of 3, a single base, so you just kept that one single base. Okay, step 3 is to set exponents equal to each other. This is step 3 right there. Once you have the same base, a single base on each side, go ahead and drop the base and set the exponents equal to each other. And then the last step would be to solve for x. And so this is step 4 right here, where we go ahead and we after step 3, it turns out to be just a regular beginning algebra equation that you can solve. So that's the solution. Now we'll look at another example. Example 2 deals with what happens when you can't use step number 1. Sometimes it's not always possible to get a common base for both sides of the equation. So we're going to have to use a different set of procedures here. We're going to have to actually use the power of logarithms. In this example, we're going to solve 12 times 3 to the 1.8 times x power equals 45. Okay, now before we actually do this, we have to, going to use what's called the change of base formula. We're not going to use it right away, we're going to use it a little bit later on, but what we'll do is we'll go to the margin here and write down what that formula is. Okay, so the change of base formula states that if you have b to the x power and that's equal to y, then since x is in the exponent, there's a way to solve for x. You write x is equal to, And then what you do is you put it's equal to a fraction. And the fraction what's in the numerator and the denominator of this fraction are both base 10 logarithms. We're using base 10 logarithms because we want to use our calculator to solve it, and we only have two bases for logarithms in our calculator, base 10 and base e, the base for the natural logarithm. So we're going to use base 10, the common base. So this is how you set it up. You have the base 10 logarithm on top divided by the base 10 logarithm on the bottom with some parentheses there that we're going to fill in here in a second. And if you look at B right here, I chose B because that stands for base, because it begins with the letter B. But there's another reason why, because if you look at the denominator of the fraction that I just wrote, B also stands for bottom. There's a B there as well. So when you're using the change of base formula, if you just remember that the base will always go in the bottom of the fraction, the denominator, inside the logarithm, then that's basically all you need to know to memorize the change of base formula. So I'm going to put B here in parentheses because that's in the bottom. And then what's left is we've got bx used. Now what's left is y, and y will go up here on top. Okay, so that's the basis. That's how we're going to. This is the change of base formula that we're going to use when we solve this equation here. Okay, so coming back to this equation, what we need to do is we have to remember that it would be a mistake to multiply 12 times 3 off the bat. Okay, 12 times 3 is 36, but we don't want to do that because of the order of operations. If you remember from algebra, that mnemonic, please excuse my dear Aunt Sally, we have to do exponents first and then multiplication after that. So because of the order of operations, since we're solving for x, what we'll need to do first is divide both sides by 12. And then we get 3 to the 1.8x power is equal to 45 divided by 12. And then 45 divided by 12 is 3.75. And then now we're ready to use the change of base formula. Our base right here is 3. That's our base. That's the B. And then 3.75 represents our y value. So if we solve for the exponent, we're going to write down 1.8 times x. That's the entire exponent. And then set it equal to a fraction with a base 10 logarithm on top and a base 10 logarithm on the bottom. So because we pointed out that 3 is the base, we just got through saying in the change of base formula that the base always goes in the bottom because base and bottom both begin with the letter B. So I'll put 3 right here, and then the y goes on top. So the 3.75 goes on top. And then to solve for x, all we have to do now is simply divide by 1.8. And so you get x is equal to this. Okay, so this would be the actual exact answer for x, but usually what we want to do is want to use your calculator to get a decimal approximation. So what we'll do is we'll use the base 10 logarithm button key on the calculator. So the base 10 logarithm, I'm just typing basically this whole fraction into my calculator. And my calculator gives me a decimal. I'm going to round it to 4 decimal places. And I get 0.6684. And this would be a numerical approximation to the value of x once you type in those logarithms into your calculator. You'll notice that the steps used to solve this equation in example 2 are different than the steps we used in example 1, because if you look at the exponents 12, 3, and 45, we were not able to get them all in the same base of 3. 45 is not a perfect power of 3, and neither is 12. So what we need to do is we had to use logarithms. So here are the steps for that. Step 1 is to isolate the power of x. Step 2 is to use change of base formula. Step 3 is to solve for x. And step 4 is to use your calculator to get a decimal approximation. So putting those steps, step 1 would be here, isolating the power of x, that's 3 to the 1.8 x power. Change of base formula is right there, number 2, step number 2. Step 3 is to solve for x. And then step 4, I type that into your calculator to get a decimal approximation. Okay, so we're going to look at our last example here. And we're going to make use of that second set of directions there where we have to use logarithms. And we're going to solve 5 times 2 to the 3x minus 1 power plus 8 equals 73. So step 1 says to isolate the power of x. This is the power of x right here. The whole thing. The base of 2 along with the exponent 3x minus 1. Okay, so to isolate that, we're going to have to subtract 8 from both sides and then divide by 5. In fact, it kind of reminds you, if you know how to solve 5y plus 8 equals 73, this equation here is related to that because the y here represents our power of x. So in a beginning algebra problem, if you have 5y plus 8 equals 73, you have to subtract 8 from both sides, you know, and you get 5y equals 65. And then you divide both sides by 5, and you get 13, y is equal to 13. You're going to do the same thing over here. You first have to subtract 8 from both sides. And then you get 5 times 2 to the 3x minus 1 equals 65. And then divide both sides by 5, and you get 2 to the 3x minus 1 power equals 13. Okay, so what we just did here is all step 1, isolating the power of x. Next we're going to use step 2, the change of base formula. And we're going to look at focus on the exponent, 3x minus 1. Write it down in step 2, 3x minus 1, and then set it equal to a fraction with a base 10 logarithm on top, a base 10 logarithm on the bottom. B stands for base and bottom, so since 2 is the base, we put that into the bottom, and then 13 is left, and that goes on in the parentheses on top. So now we have to solve for x, which will be step 3, and to solve for x here we're going to have to add 1 to both sides of the equation, and then to divide both sides by 3. So I'll do those in one step. So I get this. So that's solving for x in step 3. I added 1 divided by 3. And then step 4 is to type this all in your calculator in the right order. So I'm typing it right now, log of 13 divided by the logarithm of 2 plus 1 divided by 3, and I get a decimal approximation of 1.5668. I'm rounding it again. The decimal goes on forever, but I'm just rounding it to 4 decimal places. And those are 3 good examples on how to solve exponential equations. So I hope you learned something today, and good luck in your studies. Take care, and bye-bye.